This talk is, it's not, I mean, it'll have some amount of concrete mathematics, but it's largely to give you an idea of what geometry is about these days. All right, so what are fields of modern geometry that people do research in? One field, at least the one that I work on, is differential geometry and its generalizations. As the name itself suggests, differential seems to remind us of calculus, differential calculus. So clearly, calculus and geometry, they intermingle in this subject. Basically, the subject of differential geometry, it deals with the study of distances and angles on curved objects, in the sense that suppose you take the surface of the Earth is round, despite what the internet may tell you. So if you want to look at distances and angles on the surface of the Earth, if you want to, maybe look at triangles and ask whether there's a sine rule, cosine rule, etc. I mean, you can do this on the surface of the Earth, you can try to do it on the surface of an ellipsoid, and so on and so forth, right? So this is the subject of differential geometry, distances and angles on very general objects. Yeah. Another area of mathematics, another area that I also work on, is algebraic geometry. Algebraic geometry, actually, even in your 10th, maybe not 10th, but at least 11th and 12th standards, you would have done some algebraic geometry, although it was not given such a fancy name. Remember, for what you might have studied conic sections, right? That is, you take a degree 2 polynomial in x and y, like ax square plus bxy plus cy square, and you set it to 0, right? This can be a circle, an ellipse, a hyperbola, a pair of straight lines, etc. Yeah, and you ask questions about how many points do two circles intersect, and how many tangents does a circle have from one point, and so on and so forth. So the study of zeros of polynomials, that is algebraic geometry. We know what zeros of degree 2 polynomials look like. You can classify them, right? I mean, you can use linear transformations. That is, you can take xy to some ax plus by and cx plus dy. You can change your coordinates linearly so that every degree 2 polynomial looks like it's in a standard form. Okay. In other words, every degree 2 polynomial, its zeros are either an empty set, they're points, or they are a pair of straight lines, or just one single straight line, or a circle, ellipse, hyperbola, or a parabola, right? Likewise, if you take a degree 3 polynomial, you can still try to play the same kind of a game, and Newton classified all these things. Degree 4 onwards, it's still open, to my knowledge, okay? Now, surprisingly, the subject of algebraic geometry also ties in with number theory. Why? Because this is also a polynomial, okay? Things like this. Topology, which is the study of shapes without taking distances, angles, straight lines, etc. into account. In other words, this, if you take a donut or a vada, as your taste may be, you can pull out a part of it and still make it look like the same. So distances, angles, everything is not preserved, but these two shapes are roughly the same, right? This is a vada if I cook it, and this is the usual thing, right? But the shape is the same, roughly. Convex geometry and linear algebra. So in other words, you study objects where the notion of a straight line makes sense, right? A convex set is a set where if you take any 2 points and you join it by a straight line, this entire straight line lies within the set. And linear algebra, you can take linear combinations, right? So the notion of linearity, wherever that makes sense, you can still think of it as geometry. And in this topic, functional analysis also is a part of this infinite dimensional linear algebra. And discrete geometry and computational geometry, basically step-by-step procedures to do all of the above. Okay, this is a very popular field these days, right? Because despite all of these seeming like they're very abstract, pure mathematical things, they actually do play a role in real life. For example, differential geometry plays a role in the study of control theory in aeronautical engineering, plays a role in robotics, and it used to play a role in protein folding, but now machine learning is doing a much better job. Algebraic geometry, in particular number theory, plays a role in cryptography, that is securing your emails. Topology does play a role in data analysis. Convex geometry, linear algebra plays a role everywhere. So the point is, you would want to implement concepts of these things on computers, right? So computational geometry is a very important branch that one counts as a branch of geometry itself. Okay? So we will only focus on this part, right? Okay. So what is non-modern geometry? What is, well, not quite ancient geometry, but yeah, what is non-modern geometry? So a very quick crash course in the history of geometry. By no means can I claim to be an expert in either geometry or its history, but it has a very rich history, going all the way back to the second millennium BC, no less. So for example, the Egyptians, when they constructed the pyramids, they used some primitive sort of trigonometry, not quite trigonometry, more of similar triangles, but they needed some primitive notion of that, right? I mean, you have some sort of a similarity kind of a problem in one of those Egyptian papyruses, okay? Because even in the Indus Valley civilization, I believe some amount of geometric things were there, seeing how regular their constructions were, and likewise in the Babylonian civilizations. What is more famous when we think of geometry is the Greek school. So Greeks, Arabs, and Chinese much later contributed to the subject. Now the point is, early geometry focused on measuring things, that is, lengths, areas, volumes, and so on, and relations between them. Right? In all civilizations, whether for religious reasons or for construction or for whatever reason, measurement was important. So that's what early geometry focused on. And to a large extent, so does modern geometry, especially differential geometry. But algebraic geometry, for example, or topology does not focus on measuring things. Okay? And it was applied to astronomy. How was it applied to astronomy? I mean, if you look at the night sky, it is like a part of a sphere, right? So if you want to find out the angular distances between stars, etc., you need some notions of geometry, navigation, and related subjects. Yeah. Now the statement of the Pythagorean theorem, which one would probably consider as some proto-differential geometry, if you will. This was known much earlier. It was known even to the Indians. But the point is, the first rigorous proof, and this was by Arius, this famous proof, you know, I mean, you just take a square like this, and basically adding up the areas of the squares. I mean, this is C, so C squared is A squared plus B squared, that kind of a thing. This proof by Arius was due to the Pythagorean school. Okay? But to be honest, Arius it's not fair to use areas to prove the Pythagoras theorem, because the Pythagoras theorem is more fundamental. You don't need the notion of an area to talk about it. You can just do it with similarity, nonetheless. So even trigonometry, some primitive notions existed quite early too. Interestingly, there's an interesting story in Wikipedia. You can look it up as to how the name sine came about. You see, if you take a circle, and if you take this chord, and if the circle's radius is r, let's say it's 1, and if this is theta, then this chord is 2 sine theta by 2. In other words, sine theta by 2 is simply half of this chord. So sine is sometimes called a half chord, and the name sine comes from Latin, and it's just a perversion of Arabic and Sanskrit and so on. So basically the bottom line is these things existed quite early. The point is, Euclid revolutionized the subject by introducing the famous axioms, which I'll talk about in a moment. Okay. So because till that point, it was not clear as to what was the definition and what you're proving, right? So before going on to Euclid's axioms, I cannot resist but make this point, and it is not really related to the rest of the talk. It is related to the first slide. In fact, the Italian Renaissance artists motivated the subject of projective geometry. Like, people among you who have attended the Olympiads might have heard of projective geometry, but it's a very interesting thing. Suppose you want to draw, let's say, the picture of a tree. Okay, what would you do? You would have a piece of canvas, and you would sit here, and this is your eye, and light rays would come. Let's pretend that it's a transparent piece of canvas. They'd come to your eye, and you would draw exactly what your eye sees, right? So for example, if you have a railway tracks, when you draw them, if you put your canvas like this, if you draw them from the front view, it will appear that the railway tracks actually meet at a point, although they don't. They're parallel, but they appear to meet, right? So depending on where you sit, where your canvas is placed, and how you look, you'll get a different picture, right? So an interesting question is, if I have two artists and they both try to draw on a piece of canvas, given this artist's picture and where this artist sits and the orientation of the canvas, can you predict the same for the second artist? This transformation, can you do this? Okay. So this is the study of projective geometry. The connection to art, it's called perspective art. And I believe even Leonardo da Vinci was quite involved in this. Okay. So this projective geometry, a massive generalization of it, leads to an area of algebraic geometry. Okay. So here, the notion of distances and angles is not important at all. Okay. So distances and angles are not preserved, of course, right? I mean, there are some things that are preserved, something called the cross ratio, if you want to look it up on Wikipedia, but certainly not distances and angles. Okay. Anyway, so this was ancient geometry. So let's, out of all of these, let's focus on this point, Euclid's axioms. Okay. All right, so the geometry that we know and love from high school and so on and so forth is Euclidean geometry. So Euclid was the first person to treat points, lines, and planes. So I believe Euclid also did some three-dimensional geometry, not just plane geometry. So he treated points, lines, and planes as undefined notions. That is, everyone is expected to know what a point, a line, and a plane is. This is how axiomatization of mathematics goes about. For instance, if you look at set theory, okay? Set theory as taught in school is unfortunately problematic. There, everything was a set, right? Any English sentence you can write about a collection of objects is a set. But that's very, it's called Russell's paradox. Not everything is a set. Okay. So you need some axioms to characterize sets. But then one of you might ask, what is a set then? If you don't define to me what a set is, what am I writing axioms about? In other words, how do you formulate what is the foundation of mathematics? So all of mathematics is simply taking a bunch of finitely many letters. I mean, actually not finitely many, taking a bunch of letters and writing sentences using those letters, keeping some rules in mind. All of mathematics is just a language. I mean, you can just teach a computer to write all of mathematics. You can just give it a bunch of axioms, namely, it needs to take letters and just keep writing those letters down one after the other whilst following certain rules. That's all mathematics is, right? So the letters, if you wish, the primitive, the alphabet of your language in Euclidean geometry is simply points, lines, and planes. And the rules that you have to follow, Euclid stated 5 rules, but unfortunately, even Euclid was not completely rigorous. It was a great attempt, but it was not completely rigorous. By modern standards, even Euclid's axioms are not rigorous. Then why do we say Euclid revolutionized the subject? Because he was the first one to even recognize the need for axioms, right? Hilbert, I mean, this was just less than 100 years ago. I mean, Euclid was in the 300 BC, roughly. Okay, so it took almost 2,000 years to formulate Euclidean geometry rigorously. And this time, if you do it correctly, you get 20 axioms. So the 3 primitive undefined notions, the letters of your alphabet, if you will, are these 3. There are 3 undefined relations between these objects. They are betweenness, that is, you can make sense of, suppose 2 points lie on a line, you can ask, when does a point lie between them? I'm not going to tell you, I mean, this is an undefined notion. This is a relation between 3 points. You say that one point lies between the 3 if, and we don't define that, but we say that B lies between A and C on the same line segment, and this notion obeys some postulates. Okay, so incidence, that is when when 2 lines intersect, so then they're said to be incidence. And congruence, that is, when is it that one line segment is the same as another, or when is it that an angle, which is defined as a collection of 2 line segments, the same as another angle. So these are primitive relations. They're not defined, but they're just assumed to be some relations that obey some postulates. Okay. Now, with these 20 axioms, the beautiful thing is we can actually define the entire real number system. That is, in these 20 axioms, you can talk about, you can take a standard length and you can define all of real numbers by using just the standard length and these axioms. Likewise, you can take a standard angle and define all of real numbers using them. Okay? So this way of doing Euclidean geometry rigorously is there in several books. For example, in this book, it is a remarkable pain in the neck to do all of these things, but you can just glance at it. It's just good for the soul, if you will. Anyway, so Euclid postulated 5 properties, which I said are not good enough, but we can just pretend that Euclid's 5 postulates are good enough for Euclidean geometry. Euclid's 5th postulate, which is the most controversial, states the following, that if I give you a line and give you any point, there is a unique line passing through this point that does not intersect this line. In other words, it is parallel to this line. Okay. Why is this a controversial postulate? Because this postulate was long thought to be a consequence of the other 4 postulates. So many mathematicians over several centuries, spent a lot of time trying to derive this postulate as a consequence of the other postulates. Okay. The problem is their efforts were completely in vain because this postulate was found by Gauss and Lobachevsky to be independent of the other postulates in the following sense that they found geometries. What do I mean by geometries? A geometry is simply a set of axioms for points, lines, and planes, okay, or just points and lines. That's a geometry is simply a set of axioms for those. I mean, of course, betweenness, congruence, all of these things included, but it's just a set of axioms. So they found geometries where all the other four postulates were obeyed, but this one was violated. Okay? This geometry was called hyperbolic geometry. Hyperbolic geometry. And the Euclid's, this axiom, recall, Euclid's fifth postulate was through every point there's a unique straight line that is parallel, right? In hyperbolic geometry, through every point not lying on the line, there are at least two straight lines that are parallel to this. So if you replace Euclid's fifth postulate by this and keep everything else intact, then you get hyperbolic geometry, okay? And hyperbolic geometry is a very, very weird geometry. I mean, obviously you can see it's rather strange. I mean, you should not picture lines in hyperbolic geometry like this. In fact, lines look more like this. Sorry. These are lines and so are these. Okay. So these curved thingies are lines in hyperbolic geometry. Okay. So, yeah, so that's why suppose I, what do I mean? Why am I drawing this? What I mean is, suppose I take a point, a line, which is a curved sort of a thing. If I take a point that's not on this line, I can draw this and this. These two quote unquote lines don't intersect this. Okay. So anyway, so this is hyperbolic geometry. And the strange thing in hyperbolic geometry is that the sum of angles of a triangle is actually less than 180 degrees. It's not obvious, but it turns out that with this postulate, you can prove this property. Okay. Anyway, so non-Euclidean geometry is the study of distances and angles, that is geometry, where one or more of Euclid's axioms are violated. Okay? So hyperbolic geometry violates only the fifth axiom. However, if you are willing to violate certain other axioms, you can get a much simpler example of a non-Euclidean geometry, namely the sphere, namely the surface of the Earth. Now, of course, you might object saying that, heck, we discovered geometry, the ancients discovered geometry by doing measurements, right? The point is that the Earth is very large, so you can pretend it is flat as long as you're in a very small region of the Earth, right? So the sphere is the simplest example. What are straight lines on the sphere? Straight lines are basically those circles having parts of circles whose center is the center of the Earth. Okay. So, for example, what is a triangle on a sphere? Well, you can take two longitudes and take the equator. This is an example of a triangle. So already you can see this is 90 degrees, this is 90 degrees, this is 90 degrees. So the sum is 270 degrees, which is larger than 180 degrees. Okay. So the sum of angles of a triangle can certainly be larger than 180 degrees. And in fact, it is always larger than 180 degrees sphere. Okay. So the analogs of standard theorems like sine rule, cosine rule, etc. I mean, lest you're thinking that there is low-hanging fruit for you to do research, not really. these standard theorems, their analogs have been proven long ago on many of these spaces, namely in hyperbolic space, on the sphere, and of course we already know in Euclidean space, right? However, these geometries are very, very strange. Okay? So for example, in hyperbolic geometry, the concept of similarity of triangles is trivial. What do I mean by this? In Euclidean geometry, if you give me a triangle, I can rescale it and get a similar triangle, right? In other words, their angles are all the same, but the lengths are different, right? Whereas you also have a concept of congruence, that is, they're basically the same triangle. You can superimpose this on this, right? So this is congruence and this is similarity. In hyperbolic geometry, these two notions coincide. In other words, two triangles are similar if and only if they're congruent. Okay? So the way that it works is as follows, roughly speaking. I mean, you can look at the reference I stated if you want to do these things in more detail. So firstly, the sum of angles of a triangle is less than 180 degrees in hyperbolic geometry. So as a consequence, if you take a quadrilateral, then the sum of its angles is certainly less than 360 degrees, because a quadrilateral is the union of two triangles, and the sum of angles is the sum of angles of these two, which is less than 360 degrees, right? Therefore, you can, if suppose you have two similar triangles, let's take this triangle and let's draw the other triangle within this, okay? Let's say they are not congruent. That is, let's say this length is strictly less than this length. So you have the sum of these three angles is the same as the sum of these three angles, which is less than 180 degrees. However, the sum of these three angles, so the sum of these three angles plus the sum of these four angles, this plus this, is equal to what? It is the sum of these three angles plus 360. Once again, this plus this is 180. That much is definitely the case. So this plus this is 180. So this plus this is 360 degrees. So 360 plus this plus this plus this is the sum of these three angles plus the sum of these four angles. In other words, the sum of the three angles of the triangle plus the sum of these four angles equals the sum of these 3 plus 360. In other words, the sum of these four angles is actually 360, but that is not allowed. Okay? So in other words, two similar triangles are congruent in hyperbolic geometry. Okay? All right. So that's great. Now you might wonder, I mean, Klein, for example, of the Klein 4 group, if some of you have taken any mathematics courses, advanced ones. So, so Klein wondered whether one can classify all kinds of such geometry. So we know the Euclidean geometry, we know this hyperbolic geometry, we know spherical geometry. Can we talk about what about all other kinds of geometries? What other kinds are there, right? So Klein suspected that somehow you can, somehow group theory plays a role. I can't get into more details without using some more language. So you just have to take me on faith. So Klein postulated a program called the Erlangen program that talks about classifying all kinds of geometries. Okay. So we are closer to the study of differential geometry. Differential geometry encompasses all of these non-Euclidean geometries. Okay? It provides a framework, a language to study all kinds of geometries. So if I give you various kinds of geometries, that is not obeying various axioms of Euclid's, or maybe more generalizations of such things, what questions can you ask? What are interesting questions to ask? Okay. So you might ask, all right, can you prove sine rule? If I give you a new kind of a geometry, can you prove sine rule? While that's a reasonable question, unfortunately, it's not a very good question to ask. The reason is, if I look at, say, the geometry on a very, very weird asymmetric surface that looks like this, okay, then this point doesn't make sense, right? What is the sine rule? The sine rule works for any triangle. It doesn't matter whether the triangle is here, whether it is here, whether it's here, it doesn't matter, right? However, if I draw a triangle here versus a triangle here, they'll look very different despite having the same angles. Even if they do have the same angles, they might have very different kinds of lengths. So there's no reason to expect that one single rule will apply to all kinds of triangles, right? The problem here is this is not very symmetric. Whereas Euclidean geometry, the sphere, hyperbolic geometry, they're all very symmetric, okay? So this is not a very good question to ask. Can you prove the sine rule? Well, not quite, but you shouldn't even expect that. Okay? So what is a good question to ask? A good question is the notion of congruence. When are two spaces with ostensibly, with what apparently look like different ways of measuring distances and angles, secretly the same? In other words, when are two triangles congruent? When you can superimpose one on the other. When are two spheres congruent? Surely this sphere and this sphere are not congruent, right? This is larger than this. So when are two spheres congruent? When you can superimpose one on the other. Akin to that, if I have two different spaces, two different shapes, you can ask when you can superimpose one on top of the other. Okay? So when are they congruent? Another question is, what is the best way of measuring distances and angles on a given space? Now, what does this even mean? This sounds like a very random question, right? The latter question might seem very stupid and very random until I tell you the following remarkable fact. As Gauss proved, there is no way to draw a map of any part of the earth. I mean, even say a map of Bangalore or Calcutta or whatever, to scale on a piece of paper. That is, if I give you a piece of paper, I mean, you might see in your atlases, in school, you would see a map, right, where India is actually one tiny little V here, Australia is a tiny blob, Russia is huge. I mean, you have South America, North America, Africa, right? You might say that, okay, I've managed to draw a map of the earth, right? The problem is this is not to scale. This is not to scale. Meaning, it might appear that India is a very small country, but in reality, actually, India is a very large country. Likewise, Australia is huge. Russia is big, but not as big as one sees in these maps, okay? So you commonly see these maps drawn in the Mercator projection, and that distorts distances, right? But this is the best you can do. You have to distort distances because Gauss proved that there is no way to draw a map that does not distort distances, okay? So in other words, the best way, whatever that means, of measuring distances on the sphere cannot be the usual Euclidean one. On a piece of paper, the best way to measure distances is the usual Euclidean one. On the sphere, the best way of measuring distances is the usual method by which we do using the length of, using angles, right? The distance between 2 points is simply this angle, okay? This way does not coincide with the Euclidean one. That's the problem, okay? So in other words, if I give you even a small part of the sphere, let us say we take a hemisphere, even on that, there are possibly two different ways of measuring distances. You can think of a hemisphere as a piece of paper, or you can think of it as a hemisphere. So what is the best possible way? Okay, that this question makes sense because if you give me one single shape, you can twist it and turn it and bend it, and you can make sure that it's the way to measure distances is very different, okay? So what is the best possible way of doing it? So these are two kinds of questions that modern geometers attempt to answer. Okay. So a large portion of research in geometry, and this area of geometry is called Riemannian geometry, it focuses on the latter question. What is the best way of measuring distances and angles on a given space? Typically, best means nicest curvature properties. What does that mean? Suppose let's do the following. Let's take a droplet of water in space. Let's say you're in the International Space Station and you just take a droplet of water. There's hardly any gravity. What will the droplet of water look like? It'll look like a sphere. Why does it look like a sphere? Because water has this nice property that it tries to minimize its, given the volume, it tries to minimize its surface area. Okay. So it looks like a sphere. All right. Now the point is that you can, if you give me any weirdly shaped object, that is, suppose you take a vada or a donut or whatever, you can ask what is the roundest possible way to measure distances on it. That is, can I twist it and turn it? Can I take my vada and can I squeeze it and so on to get to make sure that it looks like the roundest possible thing, the most symmetric, the nicest, the best, the least curved possible thing, right? So that is the kind of question one tries to answer. I mean, I know this is not very clear, but we don't have much time, but I'll try to make at least a part of this a little clear. So the Poincare conjecture, for example, if you've heard of it, is a special case of such a question. So is the Calabi conjecture that fetched Yao the Fields medal. Okay, these sorts of questions typically boil down to partial differential equations, and this is, by the way, what I do: study partial differential equations that arise precisely out of this question. Anyway, so let me try to be a little rigorous and give you a slightly more concrete idea of what I'm talking about. So differential geometry studies geometry on curved objects, like the surface of the Earth, for example. The very definition of what it means to be curved is not trivial. Why is it not trivial? Because if I take a piece of paper, it's not curved, right? What if I take a piece of paper and make a small cylinder out of it by taking this edge and just bending it and just attaching this edge to this one? Okay. Now I get something that looks like it is curved, but honestly, it's not really curved. As in the geometry, if I draw, let's say a line with a certain length here, it'll go to some sort of a thing, but it has the same length. That's the problem. Okay, so it looks like it's curved, but it really isn't. Okay, so how does one define curvature? Okay, so the key point here is that the reason the cylinder looks curved is because we are looking at it from outside. If we were an ant sitting on a cylinder, let's say a part of the cylinder, not the entire one, let's say if we were an ant, we couldn't really have made out whether it was this piece of paper or the cylinder. Okay, the reason we are able to make out is only because we are outside. We are able to experience 3 dimensions, not just 2. Okay, but that is cheating. That is not what we want to study. We want to study intrinsic curvature. Okay, the curvature should come directly. An ant sitting on your surface should be able to measure this curvature. Okay, so in other words, if an ant is moving on this with a certain curve, what we should care about is tangential properties, not normal properties. So what do I mean? So suppose gamma is a smooth unit speed curve in R3. What does unit speed mean? That means the velocity has magnitude 1 for all time. Okay? Smooth means that it's differentiable as many times as you want. Okay? That means gamma is simply a function from 0, 1 to R3, which is differentiable as many times as you want, and its velocity speed is 1. Then gamma prime is the velocity, gamma double prime is the acceleration. The magnitude of the acceleration is called the curvature of the curve. Why is it reasonable to call the acceleration of a particle moving with unit speed as the curvature of its trajectory? Why? For circular motion, for example, the centripetal acceleration is v square over r, and v is 1, so it is 1 over r, where r is the radius of the circle, right? If I take a general curve, presumably the curvature should measure what a circle that just touches this curve up to a certain order, what its radius looks like. Okay. In other words, if I write the second order Taylor expansion of the curve, that's where I'll get this term from. That will tell me this. Okay. So the curvature of a large circle, what does a large circle look like? It looks like this. So it's almost a straight line, right? It's small, and that of a small circle is large. So it is fairly reasonable to talk about the curvature of a circle as reciprocal to its radius rather than the radius itself. And that's why we declare the acceleration of a curve, of a unit speed curve, to be its curvature. Okay, so that's why this definition is a reasonable definition. Now suppose S in R3 is a smooth surface. What is a surface? A surface is simply, a curve is a map from 0, 1 to R3. A surface is a map from an open set in R2 to R3. Basically, for a curve, x, y, and z are functions of one parameter, namely time. For a surface, they're functions of 2 parameters, u and v. Right? For the Earth, for example, you can use latitude and longitude. A smooth surface is one that does not look like this, that does not have sharp corners. How do you know whether there's a sharp corner or not? Well, what goes wrong here is you can't draw a unique normal. Everywhere else you can draw a normal, but here you can't. Okay? So near every point on the surface, we can parameterize the surface with 2 parameters u and v, such that the cross product of the 2 is non-zero. That is, the unit normal makes sense. This is the normal, and if it is non-zero, you can divide by its length and talk about the unit normal. Okay. So note that if f is a smooth function such that its gradient is non-zero, then the level set is a smooth surface. So ignore this point. Don't worry too much about it. All I'm trying to say is, how do you define the sphere? You set this function to a constant, right? You can very well imagine that instead of x squared plus y squared plus z squared, you can take some function f of x, y, z and set it to a constant, and you can hope to get a surface. Unfortunately, you will not always get a smooth surface. That's all I'm saying. But don't worry about this point. Okay, don't worry. Let's move on. So our aim is to define the curvature of a smooth surface at every point. Okay, so what should we do? Take all the unit speed curves. We are ants on the surface. So an ant moves at unit speed on the surface. So you can get, an ant can move in various sorts of directions along the surface, right? Now the ant has to recognize that it is on a curved object. So if it is moving with unit speed, if it has an acceleration, okay, then already maybe it is on a curved object, right? I mean, in Euclidean space, if you're moving with unit speed, you should not be having any acceleration unless you change your direction, right? In other words, unless the ant is changing its direction, it should not see any acceleration. It should see acceleration only if it's on a curved surface. However, if it changes its direction, again, all bets are off, right? So consider the acceleration's normal component, because the tangential component can arise because the ant is changing its direction. But the normal component, the component perpendicular to the surface of the acceleration, cannot arise unless the surface is genuinely curved. Okay? So the product of the maximum and minimum such numbers is called the Gaussian curvature of S at P. So you take all possible ant paths of unit speed, take all possible accelerations and take their normal components, take the maximum of such numbers and minimum of such numbers, their product is called the Gaussian curvature. Okay. All right. Now, I'll just skip this part. Don't worry about this. I can just send you these slides if you want to look at them. So let's do a couple of examples. As Claude Lebrun, Stony Brook said, what's mathematics without examples? So the Gaussian curvature of the plane z equals 0, so that's just a plane, a piece of paper, if you will, is 0. Why? Because I can surely, if I take any ant moving with unit speed, its acceleration can never have a normal component. I'll leave this to you as an exercise, but it's so. In other words, the product is always 0, the maximum and minimum curvatures. You take a sphere, x square plus y square plus z square equals r square. You can prove that the Gaussian curvature is 1 over r square, and this number is independent of where you are on the sphere. In other words, every point on the sphere looks like every other point. Okay. By the way, you see something very, very interesting here. It varies as 1 over r square, right? What is 1 over r square times 4 pi r square? It is 4 pi. In other words, this number is independent of r. And this is not a coincidence, by the way. Okay? We'll come to it later, if time permits. If you take a cone, this thing, you can form a cone out of a piece of paper. How? You can take a piece of paper and you can roll it up just like, if in Vizag at least, this chap on the beach, he rolls up a piece of paper and puts some edible items in them near the beach. So you can roll it up and form this. So in other words, you should expect that this should have 0 curvature. Indeed, if you calculate, it turns out it's 0. However, the problem is there is a sharp corner here. So the geometry of a cone is not the same as the geometry of a piece of paper because of the sharp corner. All the curvature is getting concentrated here. That's the problem. Okay. All right. So let me, in the interest of time, let me just quickly move on to a rigorous statement of Gauss's theorem. The remarkable thing, egregium, egregious these days means shocking, but back in the day it meant remarkable, is that this number, the Gaussian curvature depends only on the infinitesimal distances on the surface. That means if you're an ant, and if you knew the distances of all sorts of curves on the surface, you can deduce the Gaussian curvature. You do not need to know what the surface looks like. You just need to know the distances on it. Okay? And not on how the surface sits. In other words, suppose we take a part of a sphere made out of an unbreakable thin material, and we deform it smoothly any way we want, the curvature remains the same. So, more precisely, suppose x of ub, y of ub, and z of ub, and x prime of ub y prime of ub and z prime of ub are two such surfaces such that if you take u to u, if you go take u to u plus du and v to v plus dv, then x, y, and z go to x plus dx, y plus dy, and y z plus dz, right? So you have a small little line here. Its length squared is this much according on this surface, and on this surface it is this much. If these two are equal for all u and v, then their Gaussian curvatures are equal. In fact, you can try to prove it on your own. The calculation is quite painful, but it does work out. Okay? I mean, what do I mean by this? What is dx? Dx is dx du plus dx dv dv, where dv is the infinitesimal change in u and dv is the infinitesimal change in v. And likewise for dy, dz, dx prime, etc. Okay? Since the sphere has positive curvature, namely 1 over r square, and the plane has zero curvature, we cannot draw a faithful map of any part of the sphere on the plane. Okay, this is what I was referring to. You cannot draw a map of any part of the earth on a piece of paper to scale. Google Maps is not to scale, by the way. That is, any way to wrap a paper around a sphere causes distortions. Okay? Right. Just wrap this thing up with this slide. So in general, given a surface, one can measure distances by putting any way of measuring distances like this. In other words, what is a surface? A surface is simply x, y, and z parameterized by two numbers, right? If I change these numbers a little bit, right, x, y, and z change a little bit, all right? So you get a tiny little line. Its length squared is going to be given by this sort of a formula, right? Now, if we take this infinitesimal parallelogram formed by these vertices, after a rotation of coordinates, we can assume that this term is not there. Okay. So in other words, the infinitesimal parallelogram's area is simply square root of the determinant of this matrix times du dv. Okay. So in other words, you can talk about the areas of infinitesimal parallelograms on the surface. Now, every nice surface without boundary, things like this, the sphere, things like this, and so on, it turns out to be a donut-like object with G holes, meaning every surface you can think of which satisfies some restrictions is either a sphere or a donut or a double donut or a triple donut and so on. Okay, this number of holes is called the genus. This is called G equals 1, this is G equals 2, G equals 3, etc. The remarkable thing is, one can, the point is, one can define this Gaussian curvature, which is a number, which is a function on the surface, times this area. You can do this integration over this domain. And it turns out that this integral is 2 pi times 2 minus 2g. For the sphere, when g is 0, it is 4 pi. Remember, 1 over r squared times 4 pi r squared. So this does not depend on how you measure distances on it. Okay, so that is a very remarkable fact. It's called the Gauss-Bonnet theorem. So this integral is always equal to this, regardless of how you measure distances. Okay. So this is just a flavor of what differential geometry looks like. I hope I've conveyed some sense of what the subject looks like. So I think I'll stop here and